Almost exactly 35 years ago, I had the opportunity to give several lectures here, same auditorium, I think, on the topic language and mind. And quite a lot has been learned in the intervening years about language and the brain, hence the mind, in the sense in which I used the term then, the term mind and mental and such terms in those lectures. Pardon? Oh, thank you. And we'll continue to use them now. Always nice to have a friend in the audience. I'm using these terms as just descriptive terms for certain aspects of the world, pretty much on a par with such descriptive terms as chemical or optical, electrical, and so on. These are terms used to focus attention on particular aspects of the world that seem to have a rather integrated character and to be worth considering for special investigation, but without any illusions that they cut nature at the joints. In those earlier lectures, I took for granted that human language can reasonably be studied as part of the world, specifically as a property of the human organism, mostly the brain, and for convenience I'll keep to that. Both then and now I'm adopting what Lyle Jenkins in a recent book calls the biolinguistic perspective. That's the framework within which the approach to language that I'm considering developed about 50 years ago. Also for convenience, I'll use the term language to refer to human language. That's a specific biological system. There is no meaningful question as to whether the communication system of bees or what might be taught to apes or mathematics or music, as to whether there's no question as to whether these are languages or whether airplanes really fly or submarines really swim, or other, or whether computers think or translate languages, or other comparably meaningless questions, many of them based on a misinterpretation of an important paper by Alan Turing a little over 50 years ago, 1950, which has spawned a large and, to my mind, mostly misguided literature, explicitly despite Turing's very explicit warning not to pursue that direction, which has apparently been overlooked. From the biolinguistic perspective, language is a component of human biology, more or less on a par with the with mammalian vision or insect navigation, and other systems for which the best theories that have been devised attribute computational capacities of some kind, what's in informal usage sometimes called rule following. So for example, contemporary text on vision describes the so-called rigidity principle. It's formulated about 50 years ago as follows. It says, if possible and other rules permit, interpret image motions as projections of rigid motion in three dimensions. In this case, later work provided substantial insight into the mental computations that seem to be involved, and when the visual system follows these rules in informal terminology. But even for very simple organisms, that's no slight task. A great many issues remain unresolved in these areas, which are quite obscure even for insects. The decision to study language as part of the world in this sense should be, in my view, uncontroversial, but it has not been. On the contrary, the assumption that this is a legitimate enterprise was rejected pretty forcefully 50 years ago, and continues to be rejected. Virtually all of contemporary philosophy of language and mind is based on rejection of the assumption. The same is true of what's called the computer model of mind that underlies a good deal of theoretical cognitive science, denied in this case not only for language but for mental faculties generally. It's explicitly denied in the technical linguistic literature in what are called Platonistic accounts of language, and also in a different way denied by the conceptualism that was devised by the same authors, inaccurately attributed to many linguists, including me. It's also apparently denied by many sociolinguists. It's incompatible with structural behavioral approaches to language. It's, little to my surprise, rejected by current studies of language by leading neuroscientists, most notably Terence Deacon in recent work, which has been favorably received by eminent biologists, again, little to my surprise. The approach, therefore, seems to be controversial, but I think the appearances are misleading. A more careful look will show, I think, that the basic assumptions are tacitly adopted even by those who strenuously reject them, and indeed have to be adopted even for coherence. I'm going to put aside this interesting topic of contemporary intellectual history, and I'll simply assume that language can be studied as part of the world. I'll continue, in other words, to pursue the biolinguistic approach that took shape about half a century ago, heavily influenced by ethology, comparative psychology, and intensively pursued then along quite a few different paths, including much of the work that claims to reject the approach. Well, assuming that, let's turn to some things that ought to be obvious. It can scarcely be denied that some internal state is responsible for the fact that I speak and understand some variety of what's loosely called English, but not, say, Hindi or Swahili. To borrow and, in fact, adapt a traditional term, we can call this a state, whatever it is that's internal to me, a state of the human faculty of language, primarily a state of the brain. We can call each such state an internalized language, in the technical literature often called an I language for simplicity, I'll call it that. It should also be uncontroversial that the faculty of language has an initial state, part of our biological endowment, which permits a certain range of options, the attainable I languages. The faculty of language then is a special property that enables my granddaughter, but not her pet kitten or chimpanzee, to attain a specific I language on exposure to appropriate data which her mind, in some obscure way, is able to extract from the booming, buzzing confusion and to interpret as linguistic experience. That's no slight task. Nobody knows how it's done, but it obviously is. More accurately, every infant acquires a complex of such states. That's a complication that I'll put aside. The expectation that language is like everything else in the organic world, and therefore is based on a genetically determined initial state that it distinguishes, say, my granddaughter from her pets, that assumption has been called the innateness hypothesis. And there's a substantial literature debating the validity of the innateness hypothesis. The literature has a curious character. There are lots of condemnations of the hypothesis, but it's never formulated, and nobody defends it. Its alleged advocates, of whom I'm one, have no idea what the hypothesis is. Everyone has some innateness hypothesis concerning language. at least everyone who's interested in the difference between an infant and, say, her pets. Furthermore, the invented term innateness hypothesis is completely meaningless. There is no specific innateness hypothesis. Rather, there are various hypotheses about what might be the initial genetically determined state. These hypotheses are, of course, constantly changing as more is learned. That all should be obvious. Confusion about these matters has reached such extreme levels that it's becoming hard even to unravel, but I'll put all that aside. The biolinguistic approach takes mental faculties to be states of the organism, in particular internal languages, I languages, that are states of the faculty of language. I'll focus on language, but most of what follows should hold as well for other cognitive faculties, and in fact for far simpler organisms, say bee communication or navigation, for example. Well, when we adopt this approach, several questions arise at once. The central one is to determine the nature of the initial and attained states. And though the matter, again, appears to be controversial, I know of no serious alternative to the thesis that these are in substantial measure computational states, whether we have in mind insect navigation or what you and I are doing right now. Again, that's held to be controversial, but since there's no alternative ideas, I don't understand why. It's held to be controversial for humans. It's not held to be controversial for, say, insect navigation, but the question's about the same. Investigation of the brain in these terms is sometimes called psychological, and it's contrasted with investigation of in terms of cells, chemical processes, electrical activity, and so on. That's called physiological. These are, again, terms of convenience. They don't have any sharp boundaries. Chemistry and physics were distinguished in pretty much similar way not very long ago. So the formulas involving complex molecules that we now study in school, these were not pretty recently considered to be, I'm quoting, merely classificatory symbols that summarize the observed course of a reaction. The ultimate nature of the molecular groupings was held to be unsolvable, and the actual arrangement of atoms within a molecule, if that even means anything, was never to be read into the formulas. I'm quoting from a standard history of chemistry. Kekulé, whose structural chemistry paved the way to eventual unification of chemistry and physics, he doubted that absolute constitution of organic molecules could ever be given. His own models, his analysis of valency and so on, were to have only an instrumental interpretation as calculating devices. Actually, large parts of physics were understood in the same way by prominent scientists, including the molecular theory of gases, even Bohr's model of the atom. In fact, only a few years before physics and chemistry were united in Linus Pauling's account of the chemical bond, America's first Nobel Prize winning chemist dismissed talk about the real nature of chemical bonds as, in his terms, metaphysical twaddle. This was nothing more than a very crude method of representing certain known facts about chemical reactions, a mode of representation only, just a calculating device. The rejection of this skepticism by a few leading scientists, whose views were incidentally condemned as a conceptual absurdity, that paved the way to the eventual unification. These are fairly recent debates. I'm talking about the 1920s. These fairly recent debates in the hard sciences, I think, have considerable relevance for today's controversies concerning computational theories of cognitive capacity. That's from insects to humans. Important topic, one that I've discussed a little bit elsewhere and I think deserves a good deal more attention than it's received. Well, with the biolinguistic approach in place, this framework in place, we want to discover the relationship between psychological states and the world as described in other terms. We want to know how computational states are related to neurophysiological states, states of the brain, or represented in them in one terminology. We also want to find out how these mental states relate to the organism external world, as for example when the motions and noises produced by a forager bee direct others to a distant flower, or when I talk about a recent trip to India, or when I say that I recently read Darwin's Descent on Man, referring to a book. All of this is called intentionality in philosophical jargon. The broad issues were raised prominently at the end of the decade of the brain, which brought the last millennium to a close. The American Academy of Arts and Sciences, at the end of the millennium, year 2000, published a volume to mark the occasion. It summarized the current state of understanding in these areas. The guiding theme of the volume was formulated by a distinguished neuroscientist, Vernon Mountcastle, in his introduction to the collection. It is, in his words, the thesis that things mental, indeed minds, are emergent properties of brains, though these emergences are not regarded as irreducible, but are produced by principles that control the interactions between lower level events, principles we do not yet understand. That same thesis has been put forth in recent years as, quoting, as an astonishing hypothesis of the new biology, a radically new idea in the philosophy of mind, the bold assertion that mental phenomena are entirely natural and caused by neurophysiological activities of the brain, opening the door to new and promising inquiries and so on. Contributors to the American Academy volume were, for the most part, quite optimistic about the prospects for overcoming the remaining gaps between psychological and physiological accounts. Mountcastle's phrase, "we do not yet understand," reflects that optimism, suggests we will soon understand. Ed Wilson wrote that researchers now speak confidently of a coming solution to the brain-mind problem. Similar confidence has been expressed for half a century, including announcements by prominent scientists, Nobel Prize winner in one case, that the brain-mind problem has already been solved. We may recall usefully similar optimism shortly before the unification of chemistry and physics. So in 1929, Bertrand Russell, who knew the sciences well, he wrote that chemical laws cannot at present be reduced to physical laws. And his phrase, "at present," like Mountcastle's word "yet," expresses the expectation that the reduction should take place in the course of scientific progress, perhaps soon. Now, in the case of physics and chemistry, it never did take place. What happened was something different and totally unexpected, namely unification of a virtually unchanged chemistry with a radically revised physics. And it's hardly necessary to stress the fact that the state of understanding and achievement in these areas 80 years ago was far beyond anything that can be claimed for the brain and cognitive sciences today, which ought to give us pause. The American Academy volume reviews many important discoveries, but the leading thesis should arouse our skepticism, not only for the reason that I just mentioned. Another reason is that the thesis is by no means new. In fact, it was formulated in virtually the same words 2 centuries ago, late 18th century, by the eminent chemist Joseph Priestley. He wrote that properties of mind arise from the organization of the nervous system itself, and those properties termed mental are the results of the organical structure of the brain, just as matter is possessed of powers of attraction and repulsion that act at a distance, contrary to the founding principles of the modern scientific revolution from Galileo to Newton and beyond. Half a century before Priestley, David Hume had casually described thought as a little agitation of the brain. And shortly after, the French philosopher-physician Cabanis wrote that the brain must be considered a special organ designed to produce thought, as the stomach and the intestines are designed to operate the digestion, the liver to filter bile, and various glands to prepare salivary juices. Lamettrie, he had similar proposals. They were suppressed at the time, but they're well known today. A century later, Darwin asked rhetorically why thought, being a secretion of the brain, should be considered more wonderful than gravity, which is a property of matter. Actually, these and many other conceptions developed from an inquiry into what was called thinking matter, in part developed from what's sometimes called by historians of philosophy Locke's suggestion, John Locke's suggestion, that is his observation in his words that God might have chosen to superadd to matter a faculty of thinking, just as he annexed effects to motion, which we can in no way conceive motion able to produce. The theological apparatus may well have been for self-defense, so Locke's correspondence suggests. By the late 18th century, the thesis was widely regarded as inescapable. Newton had demonstrated, to his considerable dismay, that matter does not exist in the sense of the Galilean revolution and of the scientists of his own day and his own sense. That being the case, the mind-body problem could no longer even be formulated, at least in anything resembling the classical form. Current formulations seem at best to restate the problem of unification of psychological and physiological approaches, and to do so in highly misleading terminology. There was no mind-body problem any more than there was a chemistry-physics problem in the 1920s. Unification of Newton's discoveries led to, they really left no coherent alternative to the conclusion that was drawn by Hume, Priestley, others, and rediscovered today in pretty much the same terms, but with the problem of emergence as unresolved as it was 2 centuries ago, and that includes the question whether this notion with its reductionist connotations is even the right notion. Maybe it's the wrong notion, as proved to be the case for chemistry and physics. The traditional mind-body problem is often ridiculed as a problem of the ghost in the machine, but that's a misconception. Newton exorcised the machine. He left the ghost completely intact. A similar observation is made very recently by 2 physicists, Paul Davies and John Gribben, concluding a book of theirs called The Matter Myth. They write that during the triumphal phase of materialism and mechanism in the 1930s, Gilbert Ryle derided mind-body dualism in a pithy reference to the mind part as the ghost in the machine. But already when he coined that pithy expression in the 1930s, the new physics was at work undermining the materialist worldview on which Ryle's philosophy was based. By the end of the 20th century, they continue, we can see that Ryle was right to dismiss the notion of the ghost in the machine, not because there is no ghost, but because there is no machine. Their point is correct, but the timing is off by at least 2 centuries, actually 3, although it did take some time for Newton's demolition of what was called at the time the mechanical philosophy, the belief that the world is a machine. It took a little time for that to enter scientific common sense. Newton himself was well aware of the conclusion and far from pleased by it. He regarded his own conclusion as an absurdity that no serious person could entertain, and he sought a way around it to the end of his life, as did prominent scientists of his day and much later, always in vain. Over time, it just came to be recognized that Newton had not only effectively destroyed the entire materialist, physicalist conception of the universe, but he had also undermined the standards of intelligibility on which the early scientific revolution was based. The outcome is familiar, at least in history of science. It was described very well in the classic 19th century History of Materialism by Friedrich Lange. He pointed out that scientists have accustomed ourselves to the abstract notion of forces, or rather a notion hovering in a mystic obscurity between abstraction and concrete comprehension, a turning point in the history of materialism that removes the surviving remnants of the doctrine far from the ideas and concerns of the genuine materialists of the 17th century and deprives them of any significance. That, too, is now a virtual truism, at least among historians of science. One of the founders of the modern discipline, Alexander Poiré, he wrote 40 years ago that a purely materialistic or mechanistic physics is impossible, and we simply have to accept that the world is constituted of entities and processes that we cannot intuitively grasp. The problems of emergence and unification take on an entirely new form in the post-Newtonian era, a form that's furthermore unstable, changing as science comes to accommodate new absurdities, as they would have been regarded by the founding figures of the scientific revolution, including Newton, and I know of no reason to suppose that the process has come to an end. It's worth pointing out that the only part of our knowledge, or what we take to be knowledge, for which we can claim much confidence, is our mental world, that is, the world of our experience. As reflective beings, humans try in various ways to make sense out of this experience. One part of this effort is sometimes called folk science, when it's conducted in a more systematic, careful, controlled way. We nowadays call it science. One standard conclusion of contemporary science is that each organism, humans in particular, reflexively develop what ethologists call an Umwelt, a particular mode of constructing and interpreting experience, given the data of sense. It's quite different for us and for bees, for example. Furthermore, there is no great chain of being. In fundamental respects, insects have richer experience and more sophisticated ways of dealing with it for action, using it for action, than humans do. Among other standard conclusions of modern science are those that Priestley and many others drew, the conclusions they drew centuries ago about thinking matter, reiterated at the end of the decade of the brain, just 2 years ago, without notable change, or maybe surprisingly, without much awareness that it's revival, not innovation. and that it's revival of something that was taken to be an unavoidable truism 2 centuries ago for quite good reasons. Given the lack of a positive, determinate account of the non-mental part of the world, of the world, what's sometimes called the physical world, talk of the hard part of the mind-body problem. In recent years, that's been taken to be consciousness conventionally. That talk of that kind is misleading at best, if it's even meaningful. It may not be. Sometimes the problem is not very clearly posed. That is, it's posed in terms of questions to which we can't even think of wrong answers. So, for example, there's no sensible answer to the question, what is it like to be me? Or what is it like to be a bat? And quoting Thomas Nagel's famous paper. There are no bad answers to that. There are no good answers, none at all. Formal semantic inquiries often take the meaning of a question to be the set of propositions that are answers to it. And if that is at least a condition on meaning, then it follows that if there are no sensible answers, the question has no meaning. Even when legitimate questions are posed, we don't have any good reason, as far as I can see, to suppose that they are intrinsically harder than lots of other problems, say the problems posed for our understanding by quantum mechanics or cosmological theories of an infinity of universes, or for that matter, by the properties of motion. We don't have any reason that I know of to question the opinions of Newton, David Hume, and other not inconsiderable figures who in various ways reached Locke's conclusion that motion has effects which we can in no way conceive motion able to produce. Even before Newton, puzzlement about motion was profound. His precursor, Sir William Petty, described springing or elastic motion as the hard rock in philosophy. Philosophy means what we call science. The obscurity was so great, Robert Boyle felt, as to prove the existence of an intelligent author or disposer of things. Even the skeptical Newtonian Voltaire felt that the impenetrable mysteries of motion proved that there must be a God who gave movement to matter, rather like Locke's suggestion. One cannot say that the hard problem was solved. It was just abandoned in the course of a significant revision of the enterprise of science. That is, the recognition that in some fundamental sense the world is just unintelligible to us, and that we have to reduce our sights to the search for intelligible theories. That's something quite different. And even that goal has been strongly contested by prominent physicists. For example, in the critique a century ago of atomic theory, or even of the idea that physics should go beyond establishing quantitative relations between observable phenomena. The significance of that shift should not be underestimated. It was recognized soon enough, for example, by David Hume, who wrote that, in his words, Newton's discoveries reveal the obscurity in which nature's ultimate secrets ever will remain. These mysteries of nature, as Hume called them, referring to the phenomena of motion, will remain beyond our cognitive reach. Perhaps we might speculate, he didn't, for reasons that are rooted in the biological endowment of the curious creature that alone is able even to contemplate these questions. Well, I did talk a little bit about these topics 35 years ago, and what's happened since, including, incidentally, my own belated self-education, inclines me to believe that what I said then should be reiterated much more forcefully and in much greater depth, and with much more explicit connections drawn to contemporary discussions about problems of language and mind. Well, let's return to the narrower question of emergence of mental aspects of the world, or perhaps the development of an account of the non-mental world that can be unified with them if the physics-chemistry model turns out to be accurate. The scale of the gap that remains and the very dubious grounds for the general optimism about overcoming it are revealed very clearly in the American Academy Symposium that reviewed the state of understanding at the end of the millennium. One leading specialist on vision, who was toward the optimistic end of the spectrum, nevertheless reminded the reader that how the brain combines the responses of specialized cells to indicate a continuous vertical line is a mystery that neurology has not yet solved, or even, for that matter, how one line is differentiated from others or from the visual surround. Semir Zeki. The AAAS journal, American Association for Advancement of Science journal, Science, a year ago they devoted an issue to neuroscience. The summary article was co-authored by Eric Kandel, Nobel laureate. It was subtitled, "Breaking Down Scientific Barriers to the Study of Brain and Mind." The article covers a lot of interesting ground, but it ends up with the conclusion that the neuroscience of higher cognitive processes is only beginning. It's surely beginning from a higher plane than was constructed by Descartes, who was in many ways the founder of modern neuroscience, but nonetheless it's still beginning. Fundamental questions remain beyond even dreams of resolution. That includes those that were traditionally considered at the heart of the theory of mind, such as, for example, choosing some action or even thinking about doing so. There's been very valuable work about narrower questions. For example, how an organism executes a plan for integrated motor action, say how a cockroach walks, or how a person reaches for a cup on the table. Well, let's return to the narrower question of emergence of mental aspects of the world, or perhaps the development of an account of the non-mental world that can be unified with them if the physics-chemistry model turns out to be accurate. The scale of the gap that remains and the very dubious grounds for the general optimism about overcoming it are revealed very clearly in the American Academy Symposium that reviewed the state of understanding at the end of the millennium. One leading specialist on vision, who was toward the optimistic end of the spectrum, nevertheless reminded the reader that how the brain combines the responses of specialized cells to indicate a continuous vertical line is a mystery that neurology has not yet solved, or even, for that matter, how one line is differentiated from others or from the visual surround. Semir Zeki. The AAAS journal, American Association for Advancement of Science journal, Science, a year ago they devoted an issue to neuroscience. The summary article was co-authored by Eric Kandel, Nobel laureate. It was subtitled, "Breaking Down Scientific Barriers to the Study of Brain and Mind." The article covers a lot of interesting ground, but it ends up with the conclusion that the neuroscience of higher cognitive processes is only beginning. It's surely beginning from a higher plane than was constructed by Descartes, who was in many ways the founder of modern neuroscience, but nonetheless it's still beginning. Fundamental questions remain beyond even dreams of resolution. That includes those that were traditionally considered at the heart of the theory of mind, such as, for example, choosing some action or even thinking about doing so. There's been very valuable work about narrower questions. For example, how an organism executes a plan for integrated motor action, say how a cockroach walks or how a person reaches for a cup on the table. But no one even raises the question of why the person or the cockroach executes one plan rather than some other one. That question is raised only for the very simplest organisms, single-cell organisms. In fact, the same is true even of visual perception, which is often considered a passive process. A couple of years ago, two cognitive neuroscientists, one a colleague of mine, published a review of research on a problem that was posed in 1850 by Helmholtz. His words, even without moving our eyes, we can focus our attention on different objects at will, resulting in very different perceptual experiences of the same visual field. There's been interesting work on that, but the phrase "at will" points to an area that's beyond serious empirical inquiry. It remains as much of a mystery as it was for Newton at the end of his life, when he was still seeking what he called a subtle spirit that lies hidden in all bodies and that might, without absurdity, account for their properties of attraction and repulsion, the nature and effects of light, sensation, and the way members of animal bodies move at the command of the will. These are all comparable mysteries for Newton, perhaps even beyond our understanding, he thought, like the principles of motion and the classical problems of the theory of mind, at least since Descartes, who incidentally also regarded them as possibly beyond human understanding. Even if we restrict ourselves to the study of mechanisms, the gaps are quite substantial. One of the leading cognitive neuroscientists, Randy Gallistel, pointed out recently that we clearly do not understand how the nervous system computes, or even the foundations of its ability to compute, even for the small set of arithmetic and logical operations that are fundamental to any computation. He happens to be talking about insects, but obviously extends beyond. In another domain, one of the founders of contemporary cognitive neuroscience, Hans Lukas Teuber, he introduced an important review of perception and neurophysiology by writing that it may seem strange to begin with the claim that there is no adequate definition of perception and to end with the admission that we lack a neurophysiological theory, though this was the most that could be said. Now, it's true that that was 40 years ago, and there were dramatic discoveries right at the time that he was writing and since, but I suspect that Teuber, who's since died, would have expressed much the same judgment today. Teuber also outlined a standard way to move towards addressing the problem of unification. He explained that his purpose in reviewing the perceptual phenomena and offering a speculative psychological account of them was because this may suggest directions in which the search for neural bases of perception should proceed, namely by clarifying the assumptions that those neural bases must satisfy. Now, that's a classic approach, along with the restriction of the scientific enterprise to more modest goals, namely intelligibility of theories rather than of the world. Another consequence of Newton's demolition of the hopes of the Galilean Revolution for a mechanical conception of the world, another one was recognition that scientific inquiry is going to have to be local in its expectations. Overarching unification may take place, but perhaps over a long term and in ways that can't be anticipated. The 18th century English chemist Joseph Black set the tone for subsequent scientific work by recommending that chemical affinity be received as a first principle, which we cannot explain any more than Newton could explain gravitation, but let us defer accounting for the laws of affinity till we have established such a body of doctrine as Newton has established concerning the laws of gravitation. And chemistry, in fact, proceeded along that course, separating itself increasingly from physics. Physics followed Newton's admonition that nature will be comfortable to herself and very simple, observing a few general principles of attraction and repulsion that relate the elementary particles of which all matter is constituted, more or less in the way that different buildings could be constructed from the same bricks. The goal was, therefore, to understand, to quantify, to reduce the whole of nature to simple laws, as Newton did for, say, astronomy. I happen to be quoting Arnold Thackeray in his history of Newtonian matter theory and the development of chemistry. He goes on to say, this was the compelling, the enticing, indeed the almost bewitching goal of much work, pursuing the thoroughly Newtonian and reductionist task of uncovering the general mathematical laws which governed all chemical behavior. There was a distinct chemical tradition, followed the path that was outlined by Joseph Black, Lavoisier, who more or less founded modern chemistry, tried to keep neutral, probably to avoid controversy, but his own work helped to found the separate chemical track. Dalton abandoned entirely the Boyle-Newton corpuscular theories of matter. He adopted the radically different view that matter could exist in heterogeneous forms with varied principles. His approach, Thackeray writes, was chemically successful and therefore enjoyed the homage of history, unlike the philosophically more coherent, if less successful, reductionist schemes of the Newtonians. By the end of the 19th century, the fields of interest of chemists and physicists had become quite distinct. Quoting a standard history of chemistry, chemistry dealt with a world consisting of some 90-odd material elements with many and varied principles and properties, while physicists handled a more nebulous mathematical world of energy and electromagnetic waves that were perceived in light, radiant heat, electricity, magnetism, later radio waves, and X-rays. The chemist's matter was discrete and discontinuous. The physicist's energy was continuous, and the gap appeared unbridgeable. Meanwhile, chemists developed a rich body of doctrine, achieving chemistry's triumphs in isolation from the newly emerging science of physics. Thackeray again. As I mentioned, the isolation ended only recently in a completely unanticipated way, not by reduction, but by unifying a radically revised physics with the bodies of doctrine that chemistry had accumulated, which had in fact provided important guidelines for the reconstruction of physics, basically, Teuber's point about perception. And that's happened often in the history of science, and we cannot know whether something similar might be required for unification of the study of brain and mind, assuming that to be a task that is within our cognitive reach, and that we don't know either. Well, I've already suggested, and will repeat, that there are interesting and important parallels between the debates concerning the reality of chemistry up to unification, which was just 65 years ago, and current debates in the philosophy of mind about the reality of the constructions of psychological approaches. The former debates, chemistry-physics, they are now understood to have been totally pointless, based on serious misunderstanding. We simply have no grasp of reality other than what our best explanatory theories can provide. If they happen to be computational theories, okay, that's reality. My own view, I've discussed it elsewhere, is that current debates, very much alive right now, are also largely pointless and for essentially the same reasons. This includes central topics of philosophy of mind and theoretical cognitive science, which those of you in the disciplines will recognize, or even in the general literature. Well, considerations of the kind that I've been reviewing, these were in the background of the so-called cognitive revolution of the 1950s, at least for some of the participants. Although it was unknown at the time, in many ways the shift of perspective brought about by the cognitive revolution actually recapitulated the first cognitive revolution of the 17th century. That includes the focus on vision and language, in the latter case adopting the biolinguistic approach. That is, shifting the focus of attention from phenomena like behavior and its products, say texts, shifting from that to the inner mechanisms that enter into producing the phenomena. That's a shift, but it's actually a shift that was taken in the 17th century. Notice again, and then there was regression for a long time. Notice again that that shift still leaves us a long way from the problems of action. That's a vastly different matter. I've myself often quoted Wilhelm von Humboldt's aphorism that the core problem of the study of language is the infinite use of finite means. So it was a leading concern of Cartesian philosophy before him, and a problem that really couldn't be posed, until, very clearly at least, until the mid-20th century, when the concepts of recursive generative procedures was fully clarified. These procedures constitute the finite means that are put to infinite use, but it's important to be aware, I don't think I've stressed this enough, it's important to be aware that despite quite a lot of progress in understanding the means that are employed for infinite use, the question of how they are used is scarcely even addressed, and it was that question that was the fundamental one for Descartes, Humboldt, and other early modern figures. And again, those questions aren't even addressed for, say, insects, let alone humans. It's reasonably clear that the human capacity for language is what's called a species property, that is biologically isolated in essential respects and close to uniform across the species. That actually seems less surprising today than it did not long ago, in the light of very recent discoveries about the very limited genetic variation among humans as compared with other primates. It suggests that we've all descended from a very small breeding group, maybe 100,000 years ago. So humans are basically identical from the point of view of, say, an outside biologist looking at us. The biolinguistic approach adopted from the start what has been called, I'll quote the recently published Encyclopedia of Cognitive Neuroscience, what's called the norm these days in neuroscience, the modular view of learning. That is the conclusion that in all animals, learning is based on specialized mechanisms, instincts to learn in specific ways. I happen to be quoting Randy Gallistel again. These organs within the brain, as he calls them, perform specific kinds of computation in accordance with specific design. Apart from extremely hostile environments, the organs change state under the triggering and shaping effect of external factors. They do so more or less reflexively and in accordance with internal design. That's the process of learning, although growth might be a more appropriate term, avoiding misleading connotations of the term learning. The language organ, the faculty of language, fits that pattern, the normal pattern. According to the best theories we have, each attainable state of the system, each I language, is a computational system that determines, generates, in a technical sense, infinitely many expressions. Each of these expressions is a store of information about sound and meaning, which is accessed by performance systems. The properties of the I language result from the interplay of several factors. One factor is individual experience, which selects among the options that are permitted by the initial state. A second factor is the initial state itself, which is a product of evolution. And a third factor is general properties of organic systems, in this case computational systems, incorporating, it's reasonable to expect, principles of efficient computation. Now, the general picture involving, crucially, the third factor is familiar in the study of organic systems generally. This classic work of Darcy Thompson and Alan Turing on organic form and morphogenesis is an illustration, big topic currently in contemporary biology. One example, current example, that might be suggestive in the present connection, present context, is recent work by Christopher Cherniak, a mathematical biologist at Maryland, who's been exploring the idea that minimization of what he calls wire length, as in microchip design, should produce what he calls the best of all possible brains. And he's tried to explain in these terms the neuroanatomy of nematodes, one of the simplest and best studied organisms, and also various pervasive properties of nervous systems, such as the fact that the brain is as far forward as possible on the body axis. He wants to try to show that that's just a property of efficient computation based on wire length minimization. Well, one can trace interest in this third factor, general properties of organisms, back to a Galilean intuition, namely Galileo's concept that, in his words, nature is perfect, from the tides to the flight of birds, and it's the task of the scientist to discover in just what sense this is true. Newton's confidence that nature must be very simple, which I quoted, that reflects the same intuition. However obscure it may be, that intuition about what Ernst Haeckel called nature's drive for the beautiful has been a guiding theme of modern science since its modern origins and with the Galilean Revolution, perhaps even its defining characteristic. It's hard to say exactly what it is, but that it's a guiding intuition is not in doubt. Biologists, however, have tended to think rather differently about the objects of their inquiry. Very commonly, they adopt what François Jacob, the Nobel laureate, his image of nature as what he called a tinkerer, which does the best it can with the materials at hand, often a pretty rotten job, as human intelligence seems to be keen on demonstrating about itself. One well-known contemporary biologist, Gabriel Dover, British geneticist, he concludes in a recent book that biology is a strange and messy business, and perfection is the last word one could use to describe how organisms work, particularly for anything produced by natural selection, though, of course, produced only in part by natural selection, as he emphasizes, and as every biologist knows, and to an extent that can't be quantified by available tools. Well, we just don't know which of these conflicting intuitions is more accurate, the Galilean intuition or, say, Jacob's intuition. And we will not know until we know the answer, and they seem very remote, those answers. The same author, Gabriel Dover, writes that we are nowhere near relieving our deepest ignorance about the biological world around us. He goes on to reserve his sharpest words for those who seek to give scientific respectability to complex behavioral phenomena in humans that we cannot even begin to investigate seriously. He calls that a sign of intellectual laziness at best and shameless ignorance at worst when confronting issues of massive complexity which far exceed the reach of contemporary science. He gives some examples, but for charity I'll ignore them. The long-term goal of investigating the third factor, that is the role of general properties of organisms in determining the faculty of language and the states it can attain, internal languages, that goal was actually formulated in the early days of the biolinguistic turn, but it was put aside as unfeasible. and attention focused on the first two factors, experience and the initial state. In technical terminology, that's called the problems of descriptive and explanatory adequacy. The latter is the question of how the initial state enters into determining the transition to the final state, the state attained. The earliest attempts 50 years ago to replace traditional or structuralist accounts of language by generative rule systems revealed very quickly that very little was known about the sound and meaning and structure of language, and that huge problems had been unwittingly swept under the rug, rather as in the days when it was assumed that bodies fall to their natural place. As has often been the case, one of the hardest steps in the development of the sciences is the first one, namely to be puzzled by what seems so natural and obvious. To gain some realistic sense of what had been overlooked was an enormous task in itself, even more so in the light of the recognition that the apparent complexity and diversity of languages that was very soon discovered just had to be an illusion. The reason for that conclusion is a standard one in biology, namely, as in the case of other organs of the body, experience can play only a very limited role in determining the state that's attained, in this case, the attained eye language. So even a young child has mastered a rich and highly articulated system of sound and meaning and structural properties that goes far beyond any evidence available, and that's shared with others who have different but also highly restricted experience. So it has to be the case that the initial state plays an overwhelming role in determining the language that the child attains in all of its aspects. Experience surely has a role, a triggering and shaping role, as in the case of other organs, but it has to be a limited one. So there's no reason to suppose that language and other higher mental faculties depart radically from everything known in the biological world. The task was to show that the apparent richness and complexity and diversity is in fact an illusion, that all languages are cast to the same mold, and that experience serves only to set options within a fixed system of principles, all determined by the initial state, much as in the case of other biological systems. Well, a great deal of the research the last 40 years in these areas has been driven by a kind of tension between descriptive and explanatory adequacy. That is, the tension between the search for true theories of eye languages, the attained state on the one hand, and a true theory of the invariant initial state of the language organ on the other. The invariant initial state is the topic of what's come to be called universal grammar. It's adapting a traditional notion to quite a new context. The search for descriptive adequacy, like a true theory of Hungarian, that leads to complex, intricate theories of particular constructions in particular languages differing from one another. In contrast, the search for explanatory adequacy seeks to find the common ground from which the existing languages and all possible others arise, given the data that are structured as experience by the operations of the initial states, again in some unknown manner. The first proposals from the 1950s suggested that the initial state, the topic of universal grammar, that the initial state provides a kind of a format for rule systems and their organization and a procedure for selecting one instantiation of the format over another in terms of its success in capturing authentic linguistic generalizations, and empirical notion that incorporates also a kind of a theory internal version of standard best theory considerations. The rules themselves at the beginning were adaptations of informal traditional notions, which had proven to be utterly inadequate when they were subjected to close examination. So that meant, for example, rules for forming relative clauses in Hungarian, or passives or in Japanese, or causatives in the Romance languages, and so on. The general approach did offer a kind of solution to the core problem of the study of language. It's sometimes called in the literature the logical problem of language acquisition. That is, how does the initial state map constructed experience to the final state? But as was emphasized, that solution holds only in principle, because in practice the conception was unfeasible because of the astronomical computational demands. Well, from about 40 years ago, attempts were made to reduce the scale of the problem by seeking valid general principles that can be abstracted from particular grammars and attributed to universal grammar, meaning to the initial state of the language faculty, leaving a residue that might be more manageable. Actually, some of those proposals were the kind of proposals that were then being explored. I reviewed in the lectures here 35 years ago. After that time, by then already there was some progress. After that time, there'd been considerable progress, but it still left the tension unresolved. That is, the general picture was somehow fundamentally defective. There was no true solution, feasible solution to the logical problem of language acquisition. Well, a possible resolution of the tension was reached after a good deal of effort about 20 years ago with the crystallization of a picture of language that marked a very sharp break from a long and rich tradition tracing back to classical India and Greece. This is sometimes called the principles and parameters approach that dispenses entirely with the core notions of traditional grammar. Notions like grammatical construction or grammatical rule. From this point of view, categories such as a relative clause or passive construction are understood to be real enough, but only as taxonomic artifacts. So, for example, aquatic organisms, which would include, say, dolphins, trout, eels, and some bacteria. It's a category, but not a biological category. The phenomenal properties of these artifacts result from the interaction of invariant principles of the initial state, faculty of language, with parameters that are finite number of parameters fixed in one or another way. It would incidentally follow that there are only finitely many possible human languages apart from idiosyncrasies and choice of lexical items, and even these are sharply constrained. That means that the problem of unfeasible search is eliminated. It's a major conclusion, if correct. The conception has now been applied to typologically different languages of just about every known kind. It's led to many discoveries, a host of new questions that were never before contemplated, sometimes suggestive answers. This principles and parameters approach is an approach. It's not a theory. Within the general approach, there are many diverse theories. There's actually a very good introduction to the topic just published by Mark Baker called Atoms of Language. He himself has made major contributions to the approach. He's been working primarily on languages that appear to be at opposite ends of the spectrum of typological possibilities, picking that on purpose, of course. Mohawk and English, that's the pair that he's studied most intensively, trying to show that although they are about as different phenomenally as two languages can be, they are in reality virtually identical, apart from very small changes in a few parameters. So that, say, a Martian observer who views humans as we view other organisms would conclude that they're essentially identical. Dialectal variants of the same language. There's been extensive work of a similar character carried out worldwide with quite revealing results. One major program funded by the European Union is studying the vast number of languages in Europe, huge number in fact, misleadingly called things like German and Italian and so on, though they're totally different languages, included by those in those characterizations. I don't, and it's being done elsewhere as well, I don't want to suggest that the approach has been established. That's very far from true, but it has been very successful as a research program, as a stimulus to empirical and theoretical inquiry. Progress towards the goals of descriptive and explanatory adequacy has far surpassed anything that precedes, not only in depth of analysis of particular languages, but also in the range of typologically different languages that have been investigated, and also new areas of linguistic structure that had barely been explored before. Related fields, such as the study of language acquisition, have also been completely revitalized within a similar framework. They now look totally unlike anything that was around 20 or 30 years ago. There are some important steps towards convergence, although it's certainly going to be a long and difficult course, even if the approach turns out to be more or less on the right track. We're far from having a clear idea of what the principles and parameters actually are, but I think it's fair to say that the study of language in the last 20 years has moved to an entirely new plane. Well, I want to pick up these topics tomorrow and then move on to the issues, particularly the role of the third factor, general properties of organisms, say something about that, and then to move on to what are called the questions of intentionality. That is the question of how language, now understood within the biolinguistic framework, relates to the rest of the world.
Professor Chomsky has agreed to take a couple of questions that were submitted by the audience. Since these questions were submitted at the beginning of the lecture, they may not have been part of what's covered today. It might be a sneak preview of tomorrow. Do you still believe that the human language faculty evolved all at once in a sudden evolutionary leap? Doesn't this conflict with the general finding that evolution is gradual?
This idea, sometimes called a monster mutation, was invented, as far as I'm aware, by Elizabeth Bates, and has been repeated by many other people. It's been attributed to me for some reason. I haven't the slightest idea why. I've never said a word about it, and I have no idea whether it's true. Nor does anyone know anything about these topics in general. Why it was invented, why it was attributed to me, you can try to figure out. The fact of the matter is no one knows anything about these things, even for much simpler questions. So, for example, one well-known fact about biological organisms is they all, above the level of bacteria, they all seem to have essentially the same body type, same body forms. And it's now kind of understood how that works. Certain regulatory genes have been, master genes have been discovered that create the forms, and it just runs through the whole organic world of animals. Well, very recent work, actually a couple of papers in Nature just a few weeks ago, show laboratory experimental work that shows how this might have happened in one monster mutation. Well, okay, maybe not. There's recent work about the evolution of the human brain, articles in Science a couple of weeks ago, suggesting, in fact, that one small mutation took place which suddenly led to explosion of brain size. Maybe not. These are, I don't have anything to say about these matters. I just repeat what's in the technical literature. But why this conception was attributed to me is a total mystery as far as I know.
I hope this is not of the same ilk. It's a do you still question again. Do you still view language as self-contained module that is independent of other cognitive systems? Wouldn't it be simple to assume that language ability is grounded in the same cognitive mechanisms as other forms of human cognition?
Well, I take for granted that the human language, I mean, it's kind of like asking whether the visual system is distinct from other systems of the body. Of course it isn't. Or say the immune system. Of course it's not distinct from the rest of the body. Like you can't cut the immune system out and leave the rest of the body. I mean, it's impossible. Every subsystem of the body that's isolated for a particular inquiry is isolated because it has a kind of an integrated character, and you think you can learn something about it. It doesn't mean that it's in a little box that you can pull out, right? So the immune system's in every cell, but it's still a system. And presumably the same is true of the language faculty. I mean, we might, it brings together many different components which come from all over the place. For example, the language faculty, what you and I are now doing, makes essential use of the delicate architecture of the bones in the middle ear. Okay, they're terrific for, wonderfully designed for understanding language. Of course, they evolved for reasons having absolutely nothing to do with language. They evolved from the fact that apparently that the skulls of early mammals, about 160 million years ago, were getting bigger. And as they got bigger, a bone in the reptilian jaw started to migrate. And for mechanical reasons, apparently, it ended up in the middle ear, which turns out to be great for language. And the same is true of, the computational principles that are at the core of language. I mean, we might discover that those are the same computational principles that are used by insects for navigation. If we did, that'd be a fascinating discovery. It would mean that it's one of the things that was recruited to form the language faculty. The idea that the language faculty is isolated from other cognitive systems just makes no sense at all. Can't be. I mean, we use the language faculty to express our thoughts, to think to ourselves, to communicate, to have and communicate attitudes, to perceive the world. Of course, it's integrated with the entire collection of cognitive faculties and other faculties. Again, the interesting question that should be asked about that question is why it says, do I still believe? Because nobody could possibly believe this. There's a huge mythology about these things which has been developed. It's kind of characteristic of studies of the human higher mental faculties. They are pursued at a level of irrationality that is just hard to deal with. If the sciences, the hard sciences had, in fact, centuries ago, the hard sciences were dealt with in a similar way, but we should be able to escape from that.
Have your views regarding poverty of the stimulus changed in light of these studies?
There are no such studies. All studies show what everybody knows in advance, that the amount of data available for language acquisition is extremely small. This notion of poverty of stimulus is a little bit like what I call the innateness hypothesis. Everyone believes in poverty of stimulus, not only for language, but for everything. I mean, what turned, there was a certain embryo once upon a time that turned into my granddaughter, okay? Why didn't it turn into a worm, let's say? I mean, is it because of the nutritional input? Like would a different nutritional input in the, to the cell have turned it into a worm? Well, nobody even takes these questions seriously. They're so idiotic. What is assumed automatically by every scientist is what's called poverty of the stimulus in the case of language. It's considered controversial in the case of human mental faculties, but taken for granted without even any discussion throughout the rest of biology because it's so obvious. I mean, it cannot possibly be that what you and I are now doing is based on early, or for that matter, late input for the environment, because there isn't any, virtually none. In fact, it's easy to demonstrate that the things that even a young child do have a statistical level that's barely at the point of noise in actual discourse. The point is kind of obvious. There's nothing to discuss about it. Everyone agrees that there is poverty of the stimulus. The only question is, well, what is the initial state that in fact, first of all, structures data as experience, which is no trivial task, and then takes that experience and almost instantaneously and reflexively, as Gallistel points out, constructs an attained state That's the problem. If somebody has some ideas about it, be my guest. It's a great topic.
You have suggested that human beings possess a language acquisition device. Is this device a real entity or a metaphor?
Well, kind of like asking whether the genetic endowment that leads to an immune system is a real system or a metaphor. I mean, we end up doing what you and I, well, let's go back to my granddaughter and her imagined pet chimpanzee. Let's suppose that the two of them are exposed to exactly the same data, okay? One of them ends up doing what you and I are now doing, the other one does nothing. Suppose that she also happens to have a pet bee, okay? Well, the pet bee and my granddaughter are exposed to the same visual data. In the case of the bee, it'll end up with a complicated, intricate system of communication that humans can't possibly duplicate. It's way beyond our cognitive capacities to communicate the distance and height and quality of a flower. Humans simply can't do that. But the bee does it reflexively. Well, observing facts like that, every scientist just takes for granted there's something special about my granddaughter or the bee and the chimpanzee which uses the same data to end up in very different states. And unless, it's miracles, that has to do with their genetic endowment. So therefore, we can talk about a language acquisition device, a chimpanzee call acquisition device, a bee communication acquisition device. These aren't metaphors. These are just descriptions of subcomponents of an organism which you try to understand. There's nothing metaphoric about them, and there really should be nothing controversial about them. I mean, unless one thinks that the bee, the chimpanzee, and my granddaughter should end up the same way with the same data. Unless anybody thinks that, then the answer should be obvious.
Is there any evidence of evolutionary change in the historical record of human language?
No. As I mentioned before, that at least current understanding is that there's extremely little genetic variation among humans as compared with other primates, meaning, which is taken to mean that we're basically all kind of cousins, coming from the same small breeding group not very long ago. Like 100,000 or 200,000 years is essentially nothing in evolutionary time. So there's just been no time for any evolution. Nobody knows exactly when language got into the picture, but probably about the same time, roughly plus or minus 100,000 years. And there's been just no time for any evolutionary change to take place. That's why, say, my granddaughter, I don't know why I'm focused on her, but my granddaughter, if she'd grown up, say, in Tokyo, would be talking perfect Japanese, because she's genetically identical to the kids who grow up in Tokyo as far as this capacity, or probably just about every capacity is concerned. So then, if that's true, there can't have been any meaningful evolutionary change in the brief history of language. It's just way too short.
Now, this is the last, and it's a very open-ended question, so feel free to ignore it or do what you like. What details or results of current neuroscience bear on your current biologically based language theories?
Well, current neuroscience is providing some new ideas, not so much neuroscience as new techniques. For example, imaging, brain imaging, is providing rather interesting suggestive results, fMRI and things like that. You don't know exactly what to make of them because, these are investigating systems that are just not understood on the basis of signals that are detected from the outside. Some of the results are quite, in a way, startling. So, for example, Proceedings of the National Academy of Sciences just recently, a couple of months ago, published a paper by Laura Petito, an investigator who's was in Montreal, now in Dartmouth. She apparently seems to have shown that sign language, deaf children who use sign, the neural centers that are involved in processing the sign are close to identical, as far as you can tell, identical with those of hearing infants who are processing auditory input. That's a very surprising result. I mean, a little less surprising than it would have been 20 years ago, because work has shown that these systems are very similar in many structural respects, but that they're neurally represented in the same place is quite interesting if it's true. It would mean that whatever our faculty of language is, it's probably independent of modality, sensory modality, some analytic computing system that could use one modality or another. The fact that, say, vision and hearing end up analyzed in the same place is a little bit surprising because of what's known about the projection of sensory systems into the cortex. But that kind of inquiry is pretty interesting and suggestive, and there is work of that kind coming along. As for neuroscience itself, remember that very little is known. I mean, I quoted the encyclopedia, the current edition of the MIT Encyclopedia of Cognitive Neuroscience, as pointing out that we do not understand the neurophysiology of even the most elementary computations that are used throughout the animal world, say for insect navigation. Even the simplest ones, the neurophysiology is completely obscure. When you try to get to human language, you're off in outer space somewhere. It's an important problem. Maybe someday it'll be understood, but it's pretty remote.
Well, thank you very much for a most stimulating lecture.